So this doesn't hold anymore. 26th. Okay, I'll post the homework and then I think about when the due. So about the homework is still being homework 7, correct? To be posted, I will not put that in. Surely not tomorrow. Okay. You think it will be okay to make it due on Thursday? So 26. If there are only a few questions on matrix diagonalization.
Today is 25. So
Sorry, 28. 25, 26 is 28 dimension. Okay.
I mean,
That'll be maybe few questions,
yeah.
right,
Confirm.
on matrix
Yeah.
diagonalization. Okay. Yes, so we want to do some basic ideas of matrices. I will assume that you all know what a matrix is. We just want to concentrate on how to find the eigenvalues and eigenvectors of a matrix. Small details, just making it concrete, that's all. So let's see. Since we need some matrices to work with, let's introduce what is called polymatrices. What are polymatrices? Are you familiar?
Yeah, it's based on the spins of the particle.
Correct. Very good. And what are they?
There are 4 polymatrices, but sigma and sigma, but I can't remember the.
Correct. 3 actually, but 4th one is the identity probably. But yeah, good. So very good. So let's say sigma x is 0, 1, 1, 0. So these are all 2 by 2 matrices. Sigma y equal to 0 minus I 0, and sigma z is equal to 0, 1. And if you want, there is a 4th identity matrix 1, 0, 0. But typically, you say these 3 are polymatrices. That's an identity matrix. But I do see these 4 together form a complete set of matrices, in the sense any 2 by 2 Hermitian matrix can be written in terms of these 4. So in that sense, the 4th matrix is a good thing to have. Okay. And so if we were to say not x, instead if we call this y, 1, 2, and 3, right? And if we use our index notation, there is this interesting property that you take any polymatrix and multiply it by any other polymatrix, right? If they are the same, if I and j are exactly the same, then that's equal to 1. So that's delta ij. That means if I is equal to j, that's equal to 1. But by any chance, if it is not the same, for example, if this is sigma 1, sigma 2, then it is given by, so there's a complex, this is the imaginary square root of -1, and this is I, j, k. So there is a cyclic property. I is 1, j is 2, then only k is equal to 3 can survive, right? So that's sigma k. So this is often called the algebra of polymatrices. Okay, this is the same as the algebra for the angular momentum, which you mentioned. This is used to represent the spin of a particle, and that is correct. So angular momentum. What's the difference between spin and angular momentum?
I can remember the equation. L equal to R plus product with P. It's perpendicular to the radius, and the spin concept is a little bit confusing for me.
Yeah, so I think what you said, this is angular momentum, this is standard, right?
Yeah.
So L is equal to R cross the P.
Yeah.
Right? That's angular momentum, but whereas spin in here, spin is also part of angular momentum.
Yeah.
You often hear this, but what's the difference between spin and angular momentum? So
there is JS or something.
yeah, what you would say is that J, so this is the correct, the J is equal.
S into S plus 1 or something.
No, that's a quantum numbers. But just as a definition, this is L plus S. Okay, so this is sum of two angular momentums. So, but what is the second angular momentum? What is the meaning of that? And the point is, P is mass times velocity, right? So M times V. Now, suppose I sit on the particle, like if there is a particle, let us say an electron, I sit on the electron. That means my reference frame is the electron itself. Okay. So with respect to me, what is the velocity of the electron?
Can you repeat the question?
Let us say there is an electron is moving around. Okay. And I, using my coordinate system, sit on the electron. So as the electron is moving around, I am also moving around, right? And now I try to measure the velocity of electron who is sitting, or whom I'm sitting on. What is the velocity of the electron that I'll measure?
0.
0, is that clear? Like Earth is moving around. We are sitting on Earth. If I were to measure the velocity of Earth, it will come out to be 0. If I go outside of the frame and see, oh, it is moving, right? So that's called a body reference system. The velocity is 0, okay? Now, if I were to measure the velocity, if the velocity is 0, what will be the angular momentum of that particle? 0, right? So in the rest frame of a particle, its angular momentum will always be 0, right? Using this definition. But it turns out for electrons and protons, for many of the particles, even in the rest frame, they have an angular momentum. Okay, that's an experimental fact. So one concludes that, so that is a quantum feature. You say that, oh, this is not the total angular momentum, because this cannot capture the property of the angular momentum that is there inside an electron. It is not because the electron is spinning, because even when you set everything to 0, even then it has that spin. So you say that is a spin plus angular momentum is a total angular momentum of a particle. Okay? This is because of motion. This is an intrinsic angular momentum. Even if you stop everything, it has an intrinsic property like mass, for example. Like mass is a property of a particle. Similarly, spin, the angular momentum associated with spin, is a property of a particle. You can do it, you cannot get rid of it. Right? So that's the definition. And that was, we'll come back to this and talk about this, but and what I was trying to say is that the three components of the angular momentum satisfy exactly the same algebra. So this is often called an algebra. Like multiply one physical quantity multiplied by another, you get third one. So those are called algebra of an operator or physical quantities. In quantum mechanics, it will turn out that as we will try to quantify these things very soon, but for the mathematical preliminary towards that, let us see what is the eigenvalues and eigenvectors of these of this matrix. So let's say this is sigma 2. No, let's take sigma 1, right? So let's say sigma 1 is equal to 0, 1, 1. For our purposes, that's just a matrix. Okay? It's of course the x component of angular momentum, the spin angular momentum, but for now it is just a 2 by 2 matrix. We would like to find solutions to the equation. Let's say sigma 1 multiplied by some vector. So we will, so this is a matrix now, right? And this will be a, let's say, a vector is equal to sigma 1 prime times a vector. Okay, so what that, let me fill this in. So there's some nomenclature here. So this is a matrix or an operator. Whenever I put a prime on the quantity, this is eigenvalue of sigma 1. So sigma 1 prime is eigenvalue of sigma 1. Is that clear? So whenever I write a prime on a quantity, it will mean it's an eigenvalue. Clearly, if this is a matrix, this will be a number. Okay, typically, this is a matrix, so which is operators are like differential operators. A times B is not B times A. But these are usually numbers. It could be a complex number, doesn't have to be real, but these are numbers. And this will be eigenvector for eigenvalues on sigma 1 prime. Okay. Just any questions at this stage? That's just a notation. I mean, just for completeness, or just so that we don't think that they are always eigenvectors. This that could be any other vector. This is when I don't write anything. This is an arbitrary vector. And by whenever I say vector, I've assumed a lot of things, right? That is a vector space and so on. So this is out of all possible vectors, this is an arbitrary vector. Like when we say R, for example, vector R is an arbitrary vector in the position space. Okay. We would like to find these quantities, sigma 1 prime and the eigenvector associated with sigma 1 prime. So let's do that. And then we'll come back to the notations and how to proceed from there. Okay. So we have just to clarify what this means, so this is sigma 1 prime is equal to sigma 1 prime, and a matrix multiplied by the vector gives you a number times a vector itself. So what does this explicitly means? This means find 0, 1, 1, 0, and find a vector. So this is by vector, I mean, let's say Z1 and Z2. Notice this could be complex numbers, right? Z1 and Z2 could be complex number, but I'm looking for very special vectors that are out of all possible vectors of this kind. I'm looking for those vectors which, when operated on this, gives me a pure number times Z1 and Z2. This is a complex number. And we have used the notation here, sigma 1 prime of this is what I want to find. So Z1 and Z2. I've not specified what exactly Z1 and Z2 is. If you notice, what are we talking about? If this was a real, like there is some vector space, so this is a complex number, right? So it is 2 coordinates here, 2 coordinates here. So it's a 4-dimensional space. So it's not easy to show it. But if you were to think of this as a space, and that's a vector, sigma 1 prime. And we are asking, in general, if I were to operate on this with a matrix, this will go, right? This will move. Like if I apply a rotation matrix on this, this will become another vector. But if it is an eigenvector, what it does is that it only increases, right? So this is sigma 1 prime times sigma 1. Is that clear? It stays in the same direction. It cannot move around. It only multiplies it by a number, by a scalar number. So its direction remains the same. So the direction of the vector remains exactly the same in the vector space, but its length changes. Like it can become smaller or bigger. Is that clear? So that's the idea of an eigenvalue equation. So this is called an eigenvalue equation. So let's find this, correct? So if we want to find this, how do we go about it? So again, let's go back to this. We are interested in finding the sigma 1 prime. So I'll say this is 0, 1, 1, 0 times Z1 times Z2 is equal to sigma 1 prime. I can write this as sigma 1 prime 0, 0, sigma 1 prime, right? If I want to write a number with a matrix, I just multiply it with an identity matrix, right? So times Z1 and Z2. Okay. Move it to the left and combine it with this. So this is 0, 0, 1, 1, 0 minus of sigma 1 prime 0, 0, sigma 1 prime times Z1, Z2 is equal to 0 now. Like if I move it to the left, so that we are looking for a vector and the eigenvalue associated with it also. We are solving for both together. So this is the same as minus sigma 1 prime 1, 1 minus sigma 1 prime. And if I want to write this, it seems, so what are we looking for here if we address this as an equation? So we're looking for Z1, we have Z2, and we're looking for sigma 1 prime also. Like, this is two equations, but we're looking for more than two quantities, right? So it seems like, oh, how do we do that? So let's see how do we proceed. Let's pretend that we know sigma 1 prime. Okay, so then there are two unknowns. So how do we solve for this? So these are two equations, right? So let me write this as two equations. So this is minus sigma 1 prime times Z1 plus Z2 is equal to 0, and Z1 minus sigma 2 prime times Z2 is equal to 0. If you have two linear equations, you can solve for them.
Sigma 1 and sigma 2.
Sigma 1 prime, sigma 1 prime. Sorry. If you have two unknown variables and we have two equations, can we solve them? Solve for them?
Two unknown variables.
Yeah, two unknowns, two equations,
Two solutions.
right? We can solve for them?
No. Okay.
Yes, no? Okay, so let's get here. So let's say 2x.
Substitution.
So let's say there is x plus y is equal to 1, right? Okay. And let's say there is 2x plus 3y is equal to 2. Okay. How many solutions does it have? X and y, can you find x and y?
Yeah.
In terms of each other.
No.
Yeah, I can.
Can you solve this equation? How about that?
Yeah.
Right?
Yeah, I can solve
So
it.
what is the solution for this?
This is 2x cancel 2y.
Yeah, if you multiply by 2
Y
and
equals
subtract them,
0.
so that's 5y is equal to 4. So that's y is equal to 4 by 5, right?
While subtracting that,
Oh,
3y
first,
will be
first
negative.
subtract, right? Sorry, 2.
Y.
Oh, I made a mistake.
Y will be 0. Right?
So multiply by 2, right?
2y.
So then subtract it out. So 2y minus 3y, so that's minus y. And I multiplied by 2, so that's 0. Right? Good. So y is equal to 0. Once y is equal to 0, x is equal to 1. Right? I'll solve for this. Okay. So that's good. So what if, let's say, so these are two equations and two unknowns, right? What if I were to now do 2x plus 2y is equal to 2? Two equations and two unknowns, right? Solve for it.
It's a parallel line.
Parallel ones. Yeah, good point. So solve for it.
Those two equations are the same.
Those two equations are the same. So we don't really have two equations, right? So we have two variables and only one equation, right? So that's not a good idea, right? So two equations, one or two unknowns, one equation, then you cannot solve it. What if you have two equations and no, two unknowns and three equations?
I think we can try. We can solve it.
Is that possible?
In three equations, I think it's possible.
Three equations is possible. Okay, so two unknowns, three equations.
Three unknown, two equations will be.
Let's have one unknown, right? So let's say
If there is three equations and two unknowns, we can solve it.
We can
three equations and two unknowns, you can solve it.
Yeah.
give me three sets of equation which have only two unknowns. Construct a set of three equations, three independent equations which have only two unknowns. Okay, so let's see. So it says x plus y is equal to 2, right? And 2x minus 3y is equal to 3, and x plus 3y is equal to 1. Right? So let's see. So first, let's use these two to solve for x and y. Okay. So yeah, so let's add these up. So this is 3x is equal to 4, right? So x is equal to 4 by 3. If x is equal to 4 by 3, y is 3 times y, 1 minus 4 by 3. Y is equal to minus 1 by 9, right? 3 minus 4 minus 1 by 9.
We don't need another.
Okay. But now let me put this in there. That should get satisfied, right?
Yeah.
So 4 by 3 minus 1 by 9. So that's into 3, 12 minus 1 over 9. That's 11 over 9. It is not equal to 2. That does not satisfy. So that's not. Okay, but then the question remains as to, can you construct two?
You mentioned the independent. If they are not independent, two of them are same, it is possible.
Okay, so two of them are the same, it is possible, right? So are these independent, let's say?
No, not a, yeah, they are. Z1 and Z2 are exchange in the first equation and the second equation.
Yeah, so, okay, how do I tell this? Okay. What I'm trying to convey is, or how about this? Yeah, let's see. Let's take one more, let me try once more, okay? So x plus y is equal to 2. There. Let me say this is 0. Okay? And 2x minus 3y is also equal to 0. Okay? What are the solutions?
X equal 3 by 2. 5 by 2, right? 0. 0 than 0. X and y should be same. 5 by 2 plus 5 by minus 5 by 2.
Both are 0, 0.
So x is equal to
Positive 5 by 2.
okay. Johnny says x is equal to 0, y is equal to 0. And Bhiyan says x is equal to
5 by 2.
5 by 2 and y is equal to
Minus 5 by 2.
minus 5 by 2. Let's try this first. 5 by 2 minus 5 by 2, that's 0. But when I put this in here, that doesn't satisfy. That's not a solution. Okay. So is x equal to 0, y equal to 0 a solution?
I think so.
Yeah, if you put here 0 plus 0 is 0, 0 plus 0 is 0. That's a solution.
Yeah.
Right. So here, if I put z1 equal to 0, z2 equal to 0, that's a solution. Right?
Yeah.
That's correct. But then any linear equation, even if the right side is 0, 0, 0 will always be a solution.
Yeah.
Right? If the right hand side is 0, 0, 0 is always a solution. So z1 is equal to 0, z2 equal to 0. So sigma 1 prime is equal to 0, right? And you can go home, right? What's so it's the end of story.
Yeah.
So That's okay, that's correct, okay? But this is a trivial solution. Is there any other solution here? Okay, let's not stick that to that, okay? So now let me change this, okay, a little bit. So let me say that 2x plus lambda y, okay, is equal to 0. Okay.
Mhm.
Now find me a solution that is not trivial. X equal to 0, y equal to 0 is surely a solution, agreed. Okay. Get me a solution that is not x equal to 0, y equal to 0.
Lambda equals -2. And
If I have to get a non-trivial solution, the lambda has to be greater than 2.
Or greater than 2.
No, smaller than 2, but it can't be 2. Because otherwise, we will get a trivial solution.
-2. It should not be -2.
Yeah. Not exactly 2. It shouldn't be 2. It can be lower than 2. It can be more than
What
2.
happens if it is 2?
What happens if say it's 0?
What is 0?
I mean, if lambda is 2, then the equation is like y 2 minus 2. So on the opposite side there is 0. So y is 0. If y is 0, x is 0, we get again the trivial solution.
Hold on, what happens when lambda equal to 2? So
If lambda equals 2, then the solution is 0.
Lambda is equal to 2, we'll get a trivial solution.
The value will be 0 x and y.
um,
But they are negative.
yeah, but okay, so let's think about this a little, okay? So if you have, let's go back to one variable, a times x is equal to 3, let's say, okay?
Mhm.
And I'm looking for x. So what is x equal to?
Value.
Immediately implies x is equal to 3 by a, right? Like whatever a is. But now let us say that's 0. Ax is equal to 0. What are the solutions?
A equal to 0 or x equal to 0.
A is equal to 0 or x equal to 0. X equal to 0 is a solution, or, right? Or A is equal to 0. If I say x equal to 0 is a trivial solution, this becomes the non-trivial solution. Okay? So now tell me, this is a generalized version of this. X and y equal to 0 is surely a solution. Give me a solution that is non-trivial. So here is what we are talking about. I would like to do this in a concrete way, but I think I'm okay. So if you have a times x plus b times y and c times x plus d times y, okay? That's two equations, right? Surely x equal to 0 and y equal to 0 is the solution. Agreed? Trivial solution. What is a non-trivial solution?
I think the determinant has to be non-zero.
Perfect, perfect, right? So the non-trivial solution is determinant of A, B, C, D has to be equal to 0, and then x and y can be anything. Okay, it doesn't matter what x and y is. This is a non-trivial solution. Right? And remember, this is nothing but A, B, C, D times x and y. So two linear equations, if the right hand side is 0, of course, x equal to 0, the vector is equal to 0 is a solution, but there is a possibility that if the other one is 0, then x and y need not be 0. Correct? Like when this is 0, x and y is anything. Could be 0, but it doesn't have to be 0. Right? X and y need not be 0. That's a non-trivial problem. That we can have a solution even though everything is equal to 0. Okay? Okay, so in that sense, now we say, oh, what's the solution of this equation, right? So we are looking for sigma 1 prime, 1, 1 minus sigma 1 prime times z1 times z2 is equal to 0. That's our eigenvalue equation, right? What is the solution for this? Of course, z1 equal to 0 is the solution. That's too trivial, and there is nothing interesting there. So we say that, oh, non-trivial solution is when determinant of minus sigma 1 prime, 1, 1 prime is equal to 0. That is, again, what we are saying is that there is a vector space. We are multiplying by a vector and getting back the vector itself, right, by a constant multiply. But if you take a 0, 0 vector, which is a point here, then of course that will work. But we are saying, is there any other solution that can work? And we'll notice that, yeah, there is a non-trivial solution. Okay, this is now easy to do. Determinant of this is minus at sigma 1 prime square, and minus 1 is equal to 0.
Oh, sorry,
Yes,
I just want to disturb you guys.
yeah.
Spray bottles, we were looking for disinfectant bottles. Please,
Oh.
if you have one. But they got
Oh, I
wipes.
think it's,
Okay, you just got wipes, no problem. Thanks, sorry to serve you.
okay. And immediately we say that sigma 1 prime is equal to plus or minus 1. And these are called eigenvalues. Like in this context, this is called eigenvalues, but these are basically, it's equivalent asking for what A, B, C, D is this non-trivial, right? It's not equal to 0 in a linear set of equations. Okay, so now we know the eigenvalues, and in general notice again, the problem was a matrix multiplied by a vector gives back a vector itself, same vector multiplied by a constant, and that constant satisfies that the eigenvalues satisfy this determinant equation, and that gives me, at least in this case, is a straightforward, simple solution. But now one can say, okay, so we said that if z1 is equal to 0, z2 equal to 0, then that's a trivial solution. Now this allows non-trivial. What are those z1 and z2?
Yeah.
Right? You mean,
Eigenvector.
can we find those eigenvectors? Right now they don't have to be 0, and let's try to find those quantities. So let's set sigma 1 prime is equal to plus 1. So let's, like, there are two solutions. Right? So let's choose one of them, and then we'll come back and choose the second one. So if sigma 1 prime is equal to plus 1, then we have our matrix equation again becomes minus 1, 1, 1, minus 1. And then there is z1 and there is z2. That's equal to 0. This is again two equations, right? So are these two equations? So this is z minus z1 plus z2 equal to 0, right? And the second one is z1 minus z2 equal to 0. Are these two equations?
Same.
Right, Fabian is nodding his head. Yeah, it is not the same equation in the sense it is not independent.
Yeah.
Right, if I multiply it by minus 1, I get second.
Second.
I have only one equation. So yeah, you cannot solve for exactly, but what can you say about it? Okay, so So let's say, so let's keep the second equal, right? So Z1 minus Z1 is equal to Z2, right? That's something you can say. Z1 is equal to Z2. Okay. Give me a solution of this. So I want to find an eigenvector which satisfies this equation. Pick any eigenvector. For example, let me set Z1 equal to 1 or Z2 equal to 1, right? Z2 is equal to 1. And then Z1 is also equal to 1. So 1, 1 is a solution. And we check that. If it is 1, 1, so let's see, minus 1, 1, 1 minus 1 multiplied by 1, 1. That's equal to minus 1, 1, 0. Yes, 1 minus 1, 0. So that works. Right? In fact, if I take 2, Z2 is equal to 2, and Z1 will again be 2, right? Again, 2 minus 2 plus 2, that will also work. So in fact, as far as whenever they are equal, that will work, right? That's perfectly fine. So that's an eigenvector. But let's make this a little more concrete. So let's say it seems like any vector is allowed, but let's look for not an eigenvector, but a normalized eigenvector. So eigenvector is this, right? So eigenvector is this. So sigma 1 prime is equal to plus 1, right? That's it. So notice the language. This is an eigenvector associated with eigenvalue plus 1. Okay. This is equal to sigma 1 or Z1 and Z1 itself. Right? Or Z1. So if, or let me write this as Z1, Z1, and then I take this out 1, 1. Right? But that's a complex number, right? So now that's good. Let's keep it there. And now let's say that I'm not interested in an eigenvector. What is a normalized eigenvector? Okay. So notice what I'm asking. There is a vector, right? Okay. Any vector there will be multiplied by, so if I know one solution, then I can multiply that, and again that would be a solution. Correct. So I say that, okay, to get that arbitrariness out, I'm going to talk about a unit vector in there, and then you would think that that arbitrariness is gone, right? So let's see. So normalized eigenvector means that Z1 square
Dividing the vector by magnitude.
Dividing the vector by the magnitude, right? Very good. So Z1 square plus Z2 square is equal to 1, correct? So the vector is here. I have to divide it by the magnitude. Okay, what do I get? So let's do that by there itself if you want. But divided by the magnitude, what do I get?
1, 1.
So 1, 1. So let's say normalized eigenvector. How should I call it? A normalized eigenvector. So normalized eigenvectors are, what should I label it as? E1, let's say, okay? E1 is equal to sigma 1 prime is equal to plus 1, right? And divided by, what is the normalized of this will be E1 over E1 star times E1, right? This is square root of it.
Yeah, because of the complex.
Because of the complex feature of that, right? So this is given as, you will do sigma 1 prime is equal to plus 1. And then I want to divide by, the complex conjugate of this is called plus 1. The same vector you basically multiply by itself. Okay, that's all. And then take a square root of that. I'm just formalizing this. You can see that directly there. It's not a, like this looks very overwhelming, but it's just making it general. Okay. So what is this equal to? So I have to divide it by the magnitude of this. What is magnitude of this quantity. So this is sigma 1 plus 1. Sigma 1 prime equal to plus 1 will be equal to, right? I have to multiply by its complex conjugate. So it is Z1 star, right? You got multiplied by Z1, and 1 times 1 times 1 times 1 will be 2, right? Is that clear? 1 horizontal, 1 vertical is 2. Is that clear? 1 1 2, right? Is that clear? Right? So that's 2. So let me clear this up. Okay. So this will be equal to sigma 1 prime is equal to plus 1 is equal to Z1 star 1 1. Is that clear?
Yeah.
Right. So sigma 1 prime equal to plus 1 multiplied by sigma 1 prime is equal to plus 1 will be equal to Z1 Z1 star Z1 1 1 1 1. Right. That's equal to 1 times 1, 1 times 1, so it's 2. So it's equal to 2 times Z1 star Z1. Okay. So using that, I will say, oh, okay, so what is square root of this? Is equal to square root of 2 times magnitude of Z1 square. So this is magnitude of Z1 square, then you take a square root, so it's Z1. Clear? Okay. So E1 was, sorry, yeah, this was my E1, right? So E1 was divided by this. Is that clear? Let me write only one. Okay. So E1 is divided by and a square root. So what is this equal to? I have to just divide it by 1 over root 2, right? So it is 1 over root 2 times Z1 divided by magnitude of Z1 times 1 1. What is Z1 divided by magnitude of Z1?
Unit vector Z1. Oh,
Z1 is a complex number.
oh, yeah, complex number.
Complex number, right? Z1 is a complex number. What's a complex number divided by its magnitude? The complex number.
Gives again complex number.
Hmm?
That will give again complex number. -5.
Yeah, but you didn't answer my question.
But you can write it as the complex part and the real
Yeah,
part
yeah.
separated.
Uh-huh.
If you write it this way.
Yeah. So what's the answer? I didn't get it. Tell this again. Yeah. Good. What is that equal to?
Okay. The only thing that is coming into mind, I can separate the real part and the complex part.
That's okay, but there's is there another way of writing a complex number instead of real and imaginary?
Yeah,
Yeah. What is that?
Polar coding.
Yeah.
IRZ.
Yeah.
Exponential, you can write it as exponential.
Exponential of I theta, right? So the idea is that if you have a complex number, you can write that as magnitude of the complex number times a phase, right? We write it as R usually then, right? So Z is magnitude of Z times a unit or this is a face basically, right? If I divide z by magnitude of z,
Exponent.
then e raised to I theta, right? The face remains, right? So here, this is basically the face, right? So this is equal to e, right? This, so that is an exponential of I theta 1. That theta 1 is a face of the complex number z1, right? Times 1 over root 2 times 1 times 1, right? So what is the normalized eigenvector? That's okay, that is surely 1, but this is off. You can choose any phase. Okay, you can choose any phase and it's a solution. So there are how many eigenvectors? There are plenty of them. We already found a plenty of them, right? But now I'm saying that normalized eigenvector. I expected that, oh, if it is normalized, I'm going to choose this to be 1. I'll be taking away the arbitrariness. But I did not, right? Still, there is a phase dependence in it. And it's okay. As far as eigenvector goes, this will go away because that's the way it is constructed, that phase goes away. Like you can always get rid of the phase, even for the normalized eigenvector. Is that clear? Yeah. And in quantum mechanics, this is typically said that if you have a wave function, it is independent of the phase. You can multiply it by a phase and you still be okay. All the physics remain the same. All the measurements do not see this. So all the wave functions, any wave function we build in quantum mechanics will be independent up to, or sorry, will be arbitrary up to a phase. If we don't worry about the phase, it is perfect. But we can multiply by anything we want exponential and still our physics will remain the same. So it's arbitrary up to a phase. Okay, is that clear? Okay, so that's, well, we did this and it seems like we went through a complicated process, but maybe we can do this in a simpler way. So just to formalize that process, it's the same thing. But so let's, the Z2, when we say sigma 1 prime is equal to minus 1, let's do that, not that way, slightly different procedure. So this time we are saying it is minus 1, so it is 1, 1, 1, 1. Is equal to 0, 0. Okay. And this time you would say Z1 plus Z2 is equal to 0. So Z1 is equal to minus Z2. But we said it's it has to be normalized. So normalized eigenvector, so normalization involves magnitude of Z1 square plus magnitude of Z2 square equal to 1. Right? That's the normalization. Okay. So now let's see. So these two equations, now there are two equations and two unknowns. So let's try to solve for that. So let's substitute Z1 equal to minus Z2 inside this. If this is true and Z1 is equal to minus Z2, again it is so Z1 is equal to minus Z2, right? So minus Z2 square plus Z2 square is equal to 1. So that's 2 times Z2 square equal to 1. So Z2 is equal to 1 over root 2. If Z2, magnitude of Z2 is 1 over root 2, magnitude of Z1 is also 1 over root 2, but what about Z1 and Z2? So you can say if magnitude of Z2 is, so this implies, how do you say this? Can I do something? Is there a simpler way? Yeah, so I think at this stage you say that Z2 is equal to 1 over root 2 up to a face, right? E raised to I theta cube. Right? If the magnitude is known, Z2 can be written in this form. So if Z2 is that, what about Z1? So that implies that Z1 is equal to minus Z2, but its face remains the same. So it's 1 over root 2 times E raised to I theta. So sigma 1 prime is equal to minus 1. The normalized, yes.
Angle are dependent.
Angle is the same because Z1 and Z2 are connected. Right? Because if Z2 is this, Z1 has to be minus of this because that's a requirement, right? So it's the same face that is coming in. But this face is different from the other face. That was sigma 1. That's a completely independent equations we had, right? So that's another face. This is another face, but these two are the same face. Right. And that's necessary because sigma 1 prime is equal to Z1, Z2, right? Z1 times Z2. That's equal to, substitute this, and this becomes E raised to I theta cube times 1 over root 2 times 1 minus 1. Substitute this here. Oh, sorry, 1 minus 1 is on top, right? Okay, clear?
Yeah.
Is this an eigenvector?
Yeah.
Yes, no? Hmm?
It is.
It is.
Without the exponential. Oh.
So it is an eigenvector of this quantity. That's what you're trying to say, without the eigenvector. Because our goal is, you're right, in thinking that, yeah, whenever I asked, is this an eigenvector, you would put this in this, and it does work, right? So it's an eigenvector with minus 1 as eigenvalue. But what about this? We said it is minus 1, 1.
There can be more than one eigenvector.
Yeah, more than one, but they should be off by. It should be off by a face.
Yeah.
So what's the point? For what theta 2 is this an eigenvector? This is true for arbitrary theta 2. I can choose any theta 2 I want. If I choose 0, then that's the eigenvector. If I choose theta 2 equal to pi, what is exponential of I pi?
Cos pi plus I can
Exponential of I pi is equal to?
cos pi plus I can pi.
And how much is that?
1 plus
1. What is the value of cos pi?
minus 1.
Minus 1.
Like this is a complex number, right? So this is 0, that's 1, that's I, that's minus 1, right? That's pi,
Minus 1.
right? So it's minus 1 pi, right? So this is equal to minus 1. So if I choose theta to be equal to pi, then that's my eigenvector, right? If I choose theta to equal to pi by 2, I can choose anything I want, correct? Is that okay? Yes. Then I'll say this is equal to minus 1 is equal to, I'll get an I here, right? Pi by 2, e raised to I pi by 2 is I, correct? So I'll get a minus 1 over root 2 times minus I times I. That's also a solution. That's also a normalized eigenvector. Normalized eigenvectors are off by a phase. It's perfectly fine. Okay, so these are not unique. Sometimes, if, for example, if I were to give, ask you to find eigenvectors in an exam, if there are 10 students, each student can choose their own phase they want, and they are all right. If they were to do an experiment, they will all get the same same energy, but eigenfunctions will be different. Okay. So that's good. So there's one more thing remaining. So if we were to summarize whatever we have as of now, any questions as of now? Any confusion?
Let's move on.
Okay, yeah. So what we have done is sigma 1 is equal to 0, 1, 1, 0. And we have tried to solve for sigma 1 multiplied by equal to, we have found the solution as sigma 1 prime is equal to plus or minus 1. And the two solutions are equal to exponential of I theta 1 times 1 over root 2, normalized vectors, 1, 1, and these are phases, arbitrary phases, and it's convenient to choose them to be 0, right? If we choose this to be 0, that's perfectly fine. That's what typically we do, like we set it to be 0, but it's not necessary, right? Okay, so now the point is, it turns out if you had a equation like this, then you can actually multiply. So let's multiply this matrix as some S times sigma 1, and I'm going to leave some gap here. Sigma 1 prime is equal, so I've multiplied by arbitrary matrix, right? So this is S times sigma 1 prime. That's okay. Right. So I started from this equation. I multiplied by a 2 by 2 matrix on the left, an arbitrary 2 by 2 matrix at this point, and that's the equation. But now let's say I do also one more thing. I do S inverse times S here. That is 1, right? S inverse S is 1. I can always introduce that. And let me interchange this. That was a number. So sigma 1 prime times S. I first multiplied by an S. It penetrates that number. And I introduced an S, sigma 1 S inverse, right? This is a new matrix. Right? And this is a new eigenvector. Agreed? So the statement is that the eigenvalue equation is unique only up to a transformation matrix S. Right? If I were to change sigma 1 to S sigma 1 S inverse and all the eigenvectors as S times sigma 1 prime, everything remains fine. If that is the case, then the point is, does there exist a matrix S where I don't have to do any work at all? It is already diagonal. Like, so does that exist? So, or find S such that S sigma 1 S inverse is equal to +1 and -1. Okay.
Okay. So
Yeah.
why do you have to find this like +1 and 0, 0 and -1?
This one?
Yeah.
Because these are the eigenvalues, right? So the point is, instead of finding the eigenvalues, can I find the matrix that gives me the diagonal values as the eigenvalues? Is that clear?
Yeah, got it.
Okay. So that's another way of finding the solution, or you can invert the whole thing. If the solution exists, does there exist a matrix which, when multiplied by the matrix in the S inverse form, it will diagonalize it. So S is called in this way the diagonalization matrix. Okay. Is that clear what I'm saying? I'm saying there exists a lot of matrices which do this, but let me find that particular S which does this job. Okay, and I will call the diagonalization matrix. And then the question comes, what is that S? Okay. And S is going, so let's check what we can do. So yeah, that's so let's have the following. Let us try. Okay. So let S be equal to, we have two eigenvectors, right? Let us construct S inverse as S inverse, whatever is on the right side, right? Okay, whatever is on the right side, let's build that using these two vectors. So that is 1/√2 times 1, 1, right? So that's my matrix. That's a column matrix. And the second column is 1/√2 times -1, 1. I can have the θ1, θ2 also inside this, but let's leave it just to simplify things. We leave that, okay? But in principle, we can bring in the θ1, θ2 also. So what is this matrix equal to? 1/√2 is there all through. So let me pull that out. This is 1, 1, -1, 1. Is that clear how I built that? These are my two eigenvectors. Okay, so I just built a new matrix out of it. Okay. So that's just a prescription I'm giving. And now let's find what is S sigma 1 S inverse. Okay. If S inverse is this, what is S? How do you find S? This is the S inverse of this matrix, right? If this is a matrix, what is the inverse matrix? How do you find that?
Adjoint.
Huh?
Adjoint of the matrix.
Adjoint of the matrix, yeah. So what is the adjoint of this matrix? So the determinant of this is 1, right?
Yeah.
So that's determinant is 1. And then you have for this piece, right? That's 1 for this is the other piece. And this is -1, but then I have to take a transpose of this. So this is 1, and this is -1, and then I have to put a transpose of this, which is equal to 1, -1, 1, 1. Let's quickly check this. And is there a 1/√2? probably, right? Oh,
Yeah.
what was the determinant here? 1 over root 2, 1 over 1 by 2. 1 by 2 plus 1 by 2, that's 1, right? So this seems to be correct. Okay, so let's see if this is really correct. So 1 over root 2 times 1 minus 1, 1, 1 times 1 minus 1, 1, 1. This should be equal to 1, right? So 1, 1. So that's, oh, that's not correct.
It's not correct.
Huh? 1, 1 minus 1 minus 1. So what is the mistake I made? Did I do something wrong? Oh, because this was supposed to have a minus 1 also here because there's a cofactor, right?
Yeah.
Is that what you were saying? Yeah,
Yeah,
we're
that
trying to
is
1. Yeah, sorry. Okay, so that's 1 and this is minus. So this is minus 1 plus 1. Okay. 1, 1, yeah, so this is 1 now. 2. And 1, 1 is 0. 0 is 2, right? And that is a 1 over root 2. And what is the determinant here of? What is the determinant of this? 1 over root 2 times 1 over root 2 is 1 over 2. And minus of that, 1 over 2 times 1 over 2. That's 1.
Root 2, I think.
What? What's the determinant of this matrix? Why is this so difficult?
SC minus B. So 1 minus 1 plus 2.
This 2? Why?
1.
1.
Yeah.
Oh, I see. Yeah. I'm doing that. Yeah. 1 times 2. 2 divided by root 2. So that's root 2. Yes. Correct. Okay. And that is 1 over root 2. That is 1 over root 2 square then. And this is good. So it's 1 over 2. So that's 1, 1. Okay. Sorry. So that works. Right. Give me one more minute. So the idea is we should check this out, right? So S is 1 over root 2 times 1, 1 minus 1, 1. This is 0, 1, 1, 0. And then we multiply by 1 minus 1, 1, 1. And then the 1 over 2. Let's quickly do this. 1 over 2 times, let me leave this alone and let me multiply this. 0, and that's 1, 0, that's 1, 1, and minus 1. So that's equal to 1 over 2 times 1, so that's 2. 1 times 1, that's 0, minus 1, so that's minus 1, 1, so that's 0, and minus 1, so that's minus 2. So that's indeed 1, 0, 0, minus 1. Notice this is the first eigenvalue, second eigenvalue, right? So S equal to this is a diagonalization matrix, which gives you the eigenvalues immediately. This, I did this for theta 1 and theta 2 equal to 0, but I don't have to. I can keep the whole thing and still it will work through, right? It will come out in terms of theta 1 and theta 2. By the time it reaches here, all of that will cancel out. Okay, so there's a lot of information in there. Simple things. We have done this before, but it's good to know the details in there. Okay, thank you.